Pick up a pinecone, turn it over in your hands, and look at the little woody scales spiraling around it, curving one way and then, crossing them, curving the other. Count the spirals going in one direction, and you will almost certainly get 8. Count the ones going the other way, and you will get 13. 8 and 13, two numbers pulled from a list that has trailed after people for 800 years. 1, 1, 2, 3, 5, 8, 13, and on it goes. You will find the very same numbers waiting in the face of a sunflower, in the skin of a pineapple, in the petals of the flowers beside your door. And somewhere along the way, someone almost certainly told you what this means, that this sequence is the secret code of the universe, the hidden rhythm behind galaxies and seashells and the human face itself. Tonight I want to take that claim apart, slowly and completely, because the truth turns out to be far stranger than the myth. Why does the universe follow the Fibonacci sequence? By the end of tonight, you will know exactly, and the answer is not the one you were promised. Get cozy, subscribe if you haven't yet, because by the end of this, the quiet pattern in a pinecone will mean something far stranger and far more beautiful than any secret code. Now, let's slowly ease into this. Part 1. The pattern you think you know. Somewhere in your house, or just outside it, there is almost certainly an object that people will tell you contains a secret. It might be a pinecone sitting in a bowl on the table. It might be a pineapple in the kitchen, or a head of Romanesco broccoli in the refrigerator with its strange green spires. It might be a sunflower leaning over a fence, its dark center packed with hundreds of seeds. Pick one of these up and turn it over in your hands, and you will find, if you look closely, that its surface is not random. There are curving lines running across it, spirals that wind in one direction, and then, crossing them, spirals that wind in the other. The seeds or the scales sit at the places where those spirals meet, arranged with a regularity that feels deliberate, almost designed, as if someone had laid each one down according to a plan. Now let me give you the plan people believe is hiding there. It begins with the simplest possible act of counting. Start with 1, add another 1, and you have 2. Add the two most recent numbers together, 1 and 2, and you get 3. Add 2 and 3, and you get 5. Add 3 and 5, and you get 8. Then 13, then 21, then 34, then 55, then 89, then 144. Each number is nothing more than the two numbers before it added together, and yet the list grows and grows, and it never stops. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. That is the Fibonacci sequence, and once you have seen it, you start to see it in places you never looked before. Count the spirals on that pinecone, the ones curving to the left, and you will very likely get 8. Count the ones curving to the right, and you will very likely get 13. 8 and 13. Two neighbors in the sequence. Count the spirals on the pineapple, and you will tend to find 5 running one way, 8 running another, 13 running a third. 5, 8, 13. Neighbors again. Count the spirals in the face of a full-grown sunflower, and if you have the patience for it, you will find 34 winding one way and 55 winding the other, or in a truly enormous head, 55 and 89. The same numbers, over and over, appearing in living things that have never met, that grew on different continents, that share no obvious reason to agree with one another. And so the story writes itself. The sequence is not just a game you can play with a pencil. It is out there, in the world, in the plants and the shells and the storms, and something must be putting it there. There is more to find once your eye is trained. Walk out to a tree and look at how the leaves climb the stem, and you will notice They do not stack directly on top of one another. Each leaf sits a little way around from the one below it, turning as it rises, so that a leaf and the one several places above it line up only after you have gone around the stem a certain number of times and passed a certain number of leaves. Count the turns, count the leaves, and those counts too tend to be Fibonacci numbers, a fact botanists noticed almost 2 centuries ago and could not fully explain. Look at the head of Romanesco broccoli, and you will see the pattern nested inside itself. Each green spire a smaller copy of the whole cone, each of those built from spirals of still smaller cones. The same arrangement repeating down through the scales, like a reflection that will not fade. Slice an apple across its middle, and the seeds sit in a 5-pointed star. Look at your own hand, and someone will eagerly point out that you have 5 fingers, that each finger has 3 bones, that the sequence is hiding even in you. Once you begin seeing it, the effect is almost impossible to switch off, and that feeling of sudden recognition is a large part of why the idea has spread so far. The numbers seem to leap out of everything, unbidden, as though a veil had been lifted and the machinery underneath were finally showing through. It is a genuinely wonderful feeling, the sense that a single simple rule might be quietly running beneath the surface of the entire living world. Hold on to that feeling, because we are going to test it hard, and where it survives the test, it will mean far more than it does right now. From that observation grows one of the most widely repeated claims in all of popular science. You have heard some version of it, I am nearly certain. The Fibonacci sequence, people say, is the fingerprint of the universe. It is nature's hidden code, the secret rhythm behind the growth of every living thing. It governs the curl of a seashell and the sweep of a galaxy's arms. It is written into the proportions of the human face and the human body, into the paintings of the great masters, into the architecture of ancient temples, into the branching of trees and the swirl of a hurricane and the double helix of your own DNA. It is, in the strongest version of the claim, the mathematics that the cosmos itself obeys. The universe, we are told, follows the Fibonacci sequence. I want to take that claim completely seriously tonight, because it deserves to be taken seriously, and because taking it seriously is the only way to discover how strange the truth actually is. Here is the difficulty. That story, the one about the universe running on a secret numerical code, is mostly wrong. Not entirely wrong, which is what makes it so interesting, but wrong in most of the specific places people point to when they tell it. The seashell they show you is not what they claim it is. The temple is not built the way they say. The face and the galaxy and the strand of DNA do not carry the code that has been assigned to them. A great deal of what you have been told is a pattern that people painted onto the world after the fact, and then admired as though the world had painted it there itself. And yet the pinecone in your hand is real. The 8 spirals and the 13 spirals are really there, and you can really count them, and they really are Fibonacci numbers, and this is not an accident or a trick of the eye. So we are left with a genuine puzzle, one that is far better than the myth it replaces. The pattern is false where it is most famous, and true where it is quietest. It is absent from the grand places we were told to look and present, in the humble ones we overlooked. And in those quiet places where it is genuinely, measurably true, there is a reason for it, a reason that has nothing to do with a cosmic code, and everything to do with a single strange number and a single strange problem that number happens to solve. By the end of tonight, you will know exactly what that reason is. You will know why a sunflower arranges its seeds the way it does, and you will know that it is doing something far more remarkable than following a sequence. You will know why the shell and the temple and the galaxy do not belong on the list, and why so many careful people convince themselves that they did. And you will know why the same number that a flower quietly settles on, without a brain or a memory or the faintest idea of what a number is, also decides which worlds survive their orbits around a distant star and holds open a lane of darkness in the rings of Saturn. The question we are chasing is the one printed on the label of this whole idea. Does the universe follow the Fibonacci sequence? The honest answer is stranger than yes and stranger than no, and to reach it, we have to start not in the heavens, but with a medieval man, a book about arithmetic, and a completely absurd problem about rabbits. Part 2. A footnote about rabbits. The name attached to this sequence belongs to a man who never thought of it as anything grand. He was born around the year 1170 in the busy port city of Pisa, on the western coast of what we now call Italy, in the same decades that the famous Leaning Tower there was beginning its slow tilt into the ground. His name was Leonardo, and history remembers him as Leonardo of Pisa, though centuries later, a historian gave him the nickname that stuck, Fibonacci, a compression of a Latin phrase meaning something like son of the Bonacci family. He was not a mystic, or a priest, or an astronomer searching the heavens for hidden order. He was, of all the unglamorous things, the son of a customs official, a merchant's boy who grew up around ledgers and coins and the daily arithmetic of trade. That upbringing is the key to everything he did. His father held a post in a trading outpost on the coast of North Africa, in the city of Bugia, in modern Algeria, and the young Leonardo travelled there and worked alongside the Arab and Berber merchants of the Mediterranean world. It was in those markets that he encountered something that would matter far more than any sequence, a way of writing numbers that was quietly superior to anything in use back home. In Europe at the time, people still counted using Roman numerals, the system of letters where you write 1 as I, 5 as V, 10 as X, 50 as L, 100 as C. It is a fine system for carving a date over a doorway, and a miserable system for doing actual arithmetic. Try multiplying the Roman numeral for 238 by the Roman numeral for 14, and you will understand why medieval merchants kept their sums on a counting board and lived in fear of mistakes. The merchants of the Islamic world had something better, a set of 10 symbols, including a symbol for nothing at all, a 0, and a way of giving each symbol a value based on its position in the number. These were the Hindu Arabic numerals, developed in India and carried west through the Arab world, the very same digits you are picturing right now when you imagine a number written down. Leonardo saw at once how powerful they were. When he returned to Pisa, he set out to explain this system to European readers, and in the year 1202, he finished the book that would make his reputation. He called it Liber Abaci, which is usually translated as the Book of Calculation. It was a thick, practical manual, page after page of how to add and subtract and multiply and divide with the new numerals, how to convert currencies, how to calculate profit and interest and the fair division of goods. It was, in the most literal sense, a math textbook for businessmen. Buried in that enormous practical volume, almost as a bit of light relief, was a small puzzle. It went something like this. Suppose you place a single pair of young rabbits, one male and one female, in a field enclosed on all sides. Suppose that a pair of rabbits takes 1 month to mature, and that from the second month onward, each mature pair produces 1 new pair every month, and suppose, as no real rabbit ever has, that none of them ever die. How many pairs of rabbits will there be in the field after a year? To answer it, you count month by month. You begin with 1 pair. After a month they have matured, but produced nothing yet, so there is still 1 pair. In the next month, they produce a new pair, so now there are 2. The next month, the original pair breeds again, while the newer pair is still maturing, giving 3. Then 5, then 8, then 13. The number of pairs each month being the number from the previous month plus the number of new pairs, which is exactly the number of pairs that were mature a month before. You see what has happened. The rabbits generate the sequence. Each month's population is the sum of the 2 months before it, because the mature breeders are last month's total, and the new babies come from the population of the month before that. 1, 1, 2, 3, 5, 8, 13, 21, and after 12 months of this absurd, deathless, perfectly punctual breeding, the field holds a specific tidy number of pairs. That was the whole of it. A charming exercise to sharpen a student's arithmetic, sitting among hundreds of other exercises about grain and cloth and money. Leonardo did not present it as a law of nature. He did not claim it governed the growth of plants or the shape of the heavens. He solved his rabbit puzzle, moved on to the next problem, and as far as we can tell, gave the sequence no special weight at all. It is worth pausing on how little fame the sequence carried for most of its life. The nickname Fibonacci was not even used in Leonardo's own time. It was pinned on him centuries later, in the 1800s, by a historian sorting through old manuscripts. For 600 years, the little rabbit puzzle sat quietly in the pages of an arithmetic book, admired by the occasional mathematician, ignored by nearly everyone else. The grand reputation it now enjoys, the talk of cosmic codes and divine proportions, is a recent coat of paint applied to a very old and very modest object. That gap between the humble origin and the enormous legend is itself a clue, and we will come back to it. There is a further wrinkle that deflates the mystique even more, and it is worth knowing. Leonardo did not actually discover this sequence. It was known centuries before him, and not to Europeans at all, but to scholars in India who were studying something with no connection to rabbits whatsoever, the rhythms of poetry. In Sanskrit verse, syllables come in 2 kinds, short ones and long ones, and a long syllable takes the same time to say as 2 short ones. If you ask how many different rhythmic patterns you can build to fill a line of a given length, the answer, it turns out, is a Fibonacci number, and the counts for each length form exactly this sequence. A scholar named Pingala hinted at the underlying idea more than 2,000 years ago. Later Indian mathematicians, Virahanka, somewhere around the 7th century, and Gopala, and the Jain scholar Hemachandra, in the centuries after, described the sequence explicitly and clearly, all of them long before Leonardo was born. In the world of Sanskrit prosody, it was sometimes called the sequence of Hemachandra. It arrived in Europe wearing an Italian name only because of who happened to write it down for European readers, not because of who first understood it. I linger on this history for a reason that matters to our whole question. The Fibonacci sequence, the thing so often described as a code written into the fabric of the cosmos, entered human awareness twice, once as a way of counting poetic rhythms, and once as a way of counting imaginary rabbits. Both times it was a human tool, invented to solve a human problem, with a clear author and a clear date, and a clear paper trail leading back to particular people in particular cities. There is nothing cosmic in that origin. If the sequence turns out to describe something real in the natural world, and in a few narrow places it genuinely does, that cannot be because the universe was reading Leonardo's book. It must be because the sequence, this simple rule of adding the last 2 numbers, is the answer to some question that the universe is somehow, in those narrow places, actually asking. And to find out what that question is, we have to look harder at the sequence itself. Because hiding inside this innocent list of whole numbers is a single number that is anything but whole and anything but innocent. Part 3. The number hiding in the sequence. Let us do something to the sequence that Leonardo himself may never have bothered to do. Instead of just listing the numbers, let us divide each one by the number just before it, and watch what happens to the answers. This is a simple thing to do, and the result is one of the quietly astonishing facts of mathematics. Take 2, and divide it by 1, and you get 2. Take 3 and divide it by 2, and you get 1.5. Take 5 divided by 3, and you get about 1.667. 8 divided by 5 is exactly 1.6. 13 divided by 8 is 1.625. 21 divided by 13 is about 1.615. 34 divided by 21 is about 1.619. 55 divided by 34 is about 1.6176. 89 divided by 55 is about 1.6182. Look at what those answers are doing. They are not wandering off in some random direction. They are closing in on a single value, hopping just above it, and then just below it, and then just above it again, each hop smaller than the last, homing in on a number that sits somewhere around 1.618. If you carried the sequence out to enormous terms, dividing some enormous Fibonacci number by the one before it, the answer would settle onto that value with a precision beyond anything you could measure, and it would never quite land, always creeping closer. There is a particular number that the ratios of Fibonacci numbers are forever approaching and never reaching, and that number, not the sequence of whole numbers itself, is the true heart of this whole story. That number has a name, several names in fact. Mathematicians call it phi, after the first letter of the name of the Greek sculptor Phidias, and it is written as a value that begins 1.618039 and then continues without end and without repetition, its digits marching off into infinity in no pattern anyone will ever find. It is often called the golden ratio, and sometimes the golden mean, and in older and more romantic writing, the divine proportion. But strip away the poetic names, and here is what it actually is. The golden ratio is what you get when you divide a line into two pieces, a longer one and a shorter one, in such a way that the whole line compares to the longer piece exactly as the longer piece compares to the shorter one. That is the defining condition. The relationship between the big and the small is the same as the relationship between the whole and the big. It is a proportion that repeats itself at two scales at once, and there is exactly one way to cut a line so that it holds, and the ratio of the pieces when you do is phi. From that innocent-sounding definition falls out a piece of algebra so clean it feels like a magic trick, and this single line is the seed of nearly everything strange we will meet tonight. If you write down the condition for the golden cut and solve it, you find that phi obeys a remarkably simple rule. Phi multiplied by itself, phi squared, is equal to phi plus 1. Read that again slowly, because it is stranger than it looks. Squaring most numbers sends them shooting off somewhere unrelated. 2 squared is 4, 3 squared is 9, but the golden ratio squared is just the golden ratio with 1 added to it. Multiplying it by itself does the same thing as simply adding 1, and there is a mirror version of the same fact. 1 divided by phi is equal to phi minus 1. Taking the reciprocal, flipping the number upside down, does the same thing as subtracting 1. This number relates to itself, under multiplication, the way ordinary numbers relate to themselves only under addition. It is self-similar in its very arithmetic, and that self-similarity is exactly why it will keep turning up in things that grow by copying their own proportions. This number had cast its spell long before anyone connected it to rabbits. The ancient Greeks knew it through geometry, because the golden ratio is woven into the shape of the 5-pointed star. Draw a regular pentagon, connect its corners with diagonals, and a 5-pointed star appears inside it, and every one of those lines cuts every other in the golden ratio, the longer piece to the shorter, always 1.618. The Greeks found this proportion so pleasing that the pentagram became a kind of secret emblem, and the geometry of the golden cut runs all through the work of Euclid, who described it around 300 years before the Common Era, calling it the division of a line in extreme and mean ratio. Almost 2,000 years after Euclid, the astronomer Johannes Kepler, the man who worked out how the planets move, wrote that geometry holds two great treasures, one being a famous theorem about right triangles, and the other being this very proportion, which he called a precious jewel. Kepler was also, as it happens, the first person we know of to notice that the ratios of the Fibonacci numbers close in on the golden ratio. The two ideas had been circling each other for centuries, waiting to be joined. Now watch the two mysteries snap together. We have a sequence of whole numbers, born from a rabbit puzzle, whose ratios crawl toward this one irrational value. And we have this irrational value, phi, defined by a golden cut of a line, obeying its strange self-referential arithmetic. Why should the rabbits know anything about the golden cut? The connection is not a coincidence, and there is a formula that makes it exact. In the 1840s, a French mathematician named Binet published, though others had found it before him, a way to calculate any Fibonacci number directly, without building up the whole sequence first. And sitting right in the middle of that formula, doing all the work, is phi. The formula says, in effect, that the enormous Fibonacci numbers are essentially just powers of the golden ratio, powers of 1.618, rounded off to the nearest whole number. Raise phi to a power and divide by a fixed constant, and you land almost exactly on a Fibonacci number. Closer and closer the further out you go. The whole numbers are the shadow. The golden ratio is the thing casting it. So the sequence and the ratio are not two separate wonders that happen to be related. They are one object seen from two sides. When you count the whole number spirals on a pinecone and find 8 and 13, and when you find that 13 divided by 8 is 1.625, creeping toward phi, you are looking at the same fact twice. The countable pattern in the world, the thing you can point at and tally, is the Fibonacci numbers. The reason behind it, whenever there is a real reason, will turn out to be the golden ratio, this endless, non-repeating value with its self-copying arithmetic. And that shifts our whole question in a subtle but crucial way. We should stop asking why the universe would follow a sequence of whole numbers, which sounds absurd the moment you say it plainly, and start asking a better question. Why would anything in the natural world care about this one specific irrational number, phi, the golden ratio, more than any other? The answer, when we finally reach it, will not be that phi is beautiful, though people have called it that for centuries. It will not be that phi is lucky or sacred or magic. The answer will be that phi is useful, in a very particular and almost paradoxical way, and that its usefulness comes from a property that sounds at first like a flaw. This number, as we will see, is the single hardest number in all of mathematics to pin down, to approximate, to trap inside a simple fraction. It is, in a precise technical sense, that we will make exact, the number that most stubbornly refuses to repeat itself or to line up with anything. And astonishingly, that refusal, that pure mathematical stubbornness, is exactly the thing a growing sunflower needs. But before we can see why a flower would need the most stubborn number in existence, we have to go out into the garden and look, very carefully and very literally, at what a flower is actually doing when it grows. Part 4. Where it is actually real. There is one place in the natural world where the Fibonacci pattern is not a myth, not a projection, not a case of wishful measuring, but a real and repeatable and measurable fact. That place is the surface of a growing plant, and the study of it has a name, phyllotaxis, from the Greek words for leaf and arrangement. Phyllotaxis is the science of how plants place things, how they arrange their leaves along a stem, their scales along a cone, their florets across the face of a flower. And when you look at it closely, with patience and a way of counting carefully, the Fibonacci numbers appear again and again, with a reliability that no amount of skepticism can wave away. Start with the sunflower, because it is the grandest example. The dark central disk of a sunflower is not one flower, but hundreds of tiny ones, each of which will become a seed, packed together into a dense mosaic. Look at that disk, and you will see the seeds swept into spiral arms, some curving clockwise and some counterclockwise, the two families crossing each other everywhere. Now do the tedious, wonderful thing and count them. Count the number of spirals winding one way, all the way around, and then the number winding the other way. In head after head, across gardens and fields and continents, the two counts come out as neighbors in the Fibonacci sequence, 34 one way and 55 the other, or 55 and 89, or in a truly giant bloom, 89 and 144. Never 34 and 51, never 60 and 90. The two numbers are always Fibonacci neighbors, always one step apart in that sequence born from the rabbits. Pick up a pinecone, and you will find the same thing at a smaller scale. The woody scales spiral around the cone, and if you count the two families of spirals, you will very often find 8 and 13. A pineapple, with its tough diamond-shaped segments, shows 3 sets of spirals at once, gentle ones and steeper ones, and the counts run 5 and 8 and 13. The bumpy heart of a daisy, the scales of a cactus, the leaves of a succulent rosette, the segments of a cauliflower, all of them tend to carry Fibonacci counts in their spirals. This is not a rare curiosity you have to hunt for. It is the ordinary condition of a huge fraction of the plant kingdom, and you can verify it yourself, this week, with nothing more than a pinecone and the willingness to count twice. To understand why this happens, we have to stop looking at the finished flower and go back to the moment of its making, to the very tip of the growing plant, where the future is being built, one piece at a time. At the growing end of a shoot, there is a small soft mound of dividing cells called the meristem, and this is the factory. Everything the plant will become, every leaf and petal and seed, begins here as a tiny bump of tissue, a bump called a primordium. The meristem pushes out these bumps one at a time, and the crucial question, the question that decides the whole pattern, is simply this. When a new bump forms at the growing tip, where around the circle does it go? What angle separates each new bump from the one that came just before it? Let me take you there, down to the scale where this decision is made. Shrink until a sunflower's growing tip is a landscape around you. You are standing at the meristem, the soft dome at the center, where the plant makes its future. It is not making seeds yet. It is making bumps, tiny mounds of tissue, one at a time, each pushed up out of the crowd. Watch one form. The next does not appear beside it, and it does not appear directly across from it. It appears about 137.5 degrees around the dome, nudged into the emptiest space available. Then the whole field creeps slowly outward as the plant grows beneath it, carrying the older bumps away from the center, and another bump rises at the tip in the next emptiest gap, again about 137 degrees on from the last. There is no ruler here, there is no memory, no counting, no plan written anywhere. There is only the rule that each new bump goes where there is the most room. Speed the growth up in your mind, and the bumps stream outward in long arcs, and those arcs curve, and they cross, and they resolve into 2 sets of spirals winding in opposite directions. If you could freeze the head and count them, you would find 34 turning one way and 55 the other. You are watching a number being written, and nothing is writing it but the geometry of each new part, keeping as far as it can from the last. That angle you just watched, 137.5 degrees, is the secret at the center of the whole phenomenon, and it is not just any angle. It has a name. It is called the golden angle, and it is the golden ratio in disguise. Take a full circle, 360 degrees, and divide it into 2 arcs in the golden proportion, the same golden cut we made on a line earlier. so that the bigger arc relates to the smaller exactly as the whole circle relates to the bigger. Do that, and the smaller arc comes out to about 137.5 degrees. The angle at which a sunflower places each new seed is the golden ratio applied to a turn instead of a line. And this is not a loose or poetic connection. Botanists have measured the divergence angle in real plants, the actual angle between one primordium and the next, and in well-behaved species, it clusters tightly around that value, often within a fraction of a single degree. The plant is hitting the golden angle with a precision that would make an engineer proud. People noticed this long before they could explain it. The word phyllotaxis was coined in the mid-1700s by a Swiss naturalist named Charles Bonnet, who catalogued the ways leaves arrange themselves around stems and saw the spiral patterns clearly. A century later, in the 1830s, two French brothers, Louis and Auguste Bravet, one a botanist and one a physicist, took the crucial step of actually measuring the angle between successive leaves and found it hovering near that same value, 137.5 degrees, in species after species. They had put a number on the pattern without yet knowing why the number should be what it was. For more than 100 years after that, the golden angle in plants was a well-documented fact in search of an explanation, one of those quiet puzzles that sit in the textbooks waiting for someone to crack them open. There is a downstream consequence worth naming, because it is the part most people actually notice first. When a plant lays out its parts at the golden angle, the counts that fall out are Fibonacci numbers, and that includes the number of petals on a flower. This is why, if you go looking, you find so many blooms with Fibonacci petal counts. Many lilies have 3 petals. Buttercups famously have 5. Many delphiniums have 8. Marigolds around 13. Asters 21. And certain daisies 34 or 55 or even 89 ray florets around their rim. These are tendencies rather than iron laws, and there are plenty of 4-petaled and 6-petaled flowers in the world. But the pull toward Fibonacci counts is real, and it is strong, and it comes straight from the angle at the growing tip. Here, then, is the fact that survives every test we will throw at it tonight. Somewhere in a garden, right now, without a brain or a nerve or the faintest notion of arithmetic, a plant is placing its seeds at the golden angle, and because it does, the spirals in its face come out as Fibonacci numbers. This is a number a flower computes without knowing what a number is. And that raises the question that will occupy us next, the question that turns this from a pretty curiosity into something close to a mystery. Of all the angles in the circle, of all the ways a plant might space its parts, why this one? Why would a sunflower, or the physics that shapes it, land on precisely the golden angle, and not on some rounder, simpler, more obvious turn? The answer is where the strangeness truly begins. Part 5. Why the plant chooses that angle. To see why the golden angle wins, we have to imagine the alternatives and watch them fail. Picture a growing tip that places each new bump not at 137.5 degrees, but at some simpler, rounder angle. Suppose it uses exactly 1/3 of a turn, 120 degrees. The first bump goes down, the second, 120 degrees around, the third another 120, and now the third bump sits directly in line with the first, because 3 steps of 1/3 of a turn bring you all the way back to the start. The fourth lands on the second, the fifth on the third, and forever after, every new bump falls into one of just 3 straight lines radiating out from the center, like spokes on a wheel. The plant would grow 3 crowded ridges of tissue, with 3 enormous empty wedges between them. It would be a disaster of packing, most of the available surface wasted, the seeds piled up in 3 lines instead of spread across the whole face. The same catastrophe happens for any angle that is a simple fraction of a turn. A quarter turn gives you 4 spokes. 2/5 of a turn gives you 5. Any time the angle divides the circle evenly, the bumps line up and the gaps open, because after a fixed, small number of steps, the pattern repeats and starts stacking new growth on top of old positions. And here is the thing that connects it all back to our strange number. The failure comes from the angle being close to a simple fraction. If you want to avoid the spokes, you want an angle that is not a simple fraction of a turn, and not even close to one. An angle that no matter how many times you step around the circle, never quite brings you back to where you started, never lets the pattern repeat and lock into lines. You want the angle whose fraction of a turn is the hardest possible fraction to approximate. You want, in other words, the most irrational number there is, applied to the circle. And that number, as we are about to see fully, is the golden ratio. The golden angle is the one angle that most stubbornly refuses to line up with itself. And because it refuses, each new bump is forced to fall into a fresh gap rather than onto an old spoke, and the whole surface fills smoothly and evenly, with no seams and no waste. This is not just a hand wave. In 1979, a mathematician named Helmut Vogel wrote down a remarkably simple model of the sunflower head. His rule had only 2 parts. Place each seed at the golden angle around from the last one, and let each seed sit a little farther out from the center than the one before, spaced so the head fills evenly. That is all. From those 2 instructions, a picture emerges on the page that is almost indistinguishable from a real sunflower. Hundreds of seeds packed at uniform density, the familiar interlocking spirals appearing on their own, the Fibonacci counts falling out without ever being asked for. Change the angle even slightly, a single degree away from the golden value, and the beautiful even packing collapses into visible spokes and gaps. The golden angle is not one good option among many. It sits at a sharp and lonely peak of efficiency, and stepping off it in either direction ruins the arrangement. The most convincing evidence of all came from an experiment that used no plants at all. Let me take you into the laboratory where it happened. Step into a laboratory in France in the early 1990s. 2 physicists, Stéphane Douady and Yves Couder, are dripping oil into a dish. The oil is magnetic, and the dish sits in a magnetic field, and each drop that falls into the center becomes a tiny magnet that pushes away from every other drop already there. Because they repel, the drops drift slowly outward from the center toward the rim, making room for the next. The 2 men change just one thing, how often the drops fall, and then they watch what the drops arrange themselves into. There is no seed here. There is no gene, no hormone, no living tissue of any kind. There is only oil and magnetism, and the simple fact that each drop shoves the others away. And yet, as the drops fall and drift and repel, they settle into 2 families of interlocking spirals, and the angle between one drop and the next comes to rest, across a wide range of timing, right near 137.5 degrees. The pattern that everyone had been told was the signature of life is forming in a puddle of oil. Watching that dish, you understand something that reorders the whole picture. The flower did not invent this pattern. It inherited it from arithmetic, from the plain geometry of things trying to stay out of each other's way. That experiment did more than mimic a sunflower. It revealed what kind of thing the golden angle really is. It is not a target the plant aims for. It is what mathematicians call an attractor, an outcome that a whole family of systems slides into on their own, from many different starting points, whenever the underlying rule is the same, and the rule here is simply that each new element wants to be as far as possible from the others. Push such a system, and it settles back. Start it messy, and it cleans itself up onto the golden angle. The sunflower, the pinecone, the dish of oil, all of them are running the same simple game of mutual avoidance. And that game has one best answer, and the answer is phi. We even know, now, how the living plant plays this game in its own chemistry. The placement of each new bump is governed by a plant hormone called auxin, which pools and flows through the growing tip. Primordia form, where auxin gathers most thickly, and each bump that forms drains the auxin from the tissue around it, leaving those neighborhoods depleted and unable to sprout the next one. So the next bump can only rise where auxin is still rich, which is precisely the spot farthest from the existing bumps, the largest open gap. The chemistry is carrying out, molecule by molecule, the very same rule of maximum avoidance that the oil drops obeyed through magnetism. Biologists traced this in detail in the early 2000s, identifying the proteins that pump auxin from cell to cell and watching the pattern break and reform when they interfered with the flow. This same picture also explains something that a rigid cosmic code theory could never account for, which is why different plants, and even different parts of one plant, show different Fibonacci pairs. The particular pair you end up counting, whether it is 8 and 13, or 34 and 55, depends on one simple physical quantity, the size of each new bump, compared to the size of the growing tip that makes it. When the bumps are large relative to the tip, only a few spirals fit, and you get small Fibonacci numbers. As a sunflower head grows, and the tip widens while the bumps stay small, more spirals can be packed in, and the counts climb the sequence in sudden discrete jumps. You can actually see this on a single sunflower. Near the outer rim, laid down when the head was young and small, the spiral counts are lower, and as you move inward toward the center, laid down later when the head was broad, the counts step up to the next Fibonacci pair. The plant is not choosing which numbers to display. It is running one rule, and the numbers are handed to it by how big it happens to be at each moment. The idea goes back further than the oil drop experiment. As early as the 1950s, a botanist named Snow proposed what he called the first available space hypothesis, the notion that each new leaf or seed simply forms in the first patch of open tissue large enough to hold it, as soon as that patch opens up at the growing edge. It sounded almost too simple to be the answer to such an elegant pattern. But that is exactly what the oil drops confirmed decades later, and exactly what the auxin chemistry turned out to implement. The most ornate and celebrated pattern in the plant kingdom is generated by the plainest rule imaginable. Take the first big enough gap, and the golden angle is nothing more than what that rule produces when it runs over and over on a growing disk. The miracle dissolves into a mechanism, and the mechanism is beautiful in a way the miracle never was. But to feel the full force of it, we have to finally understand what it means to call phi the most irrational number in the world, because that phrase is doing more work than it seems. Part 6. The most irrational number. We keep saying that phi is the most irrational number, and it is time to make that phrase mean something exact, because it is the hinge on which the whole explanation turns. To call a number irrational simply means it cannot be written as a fraction, as one whole number divided by another. The square root of 2 is irrational. Pi is irrational. Phi is irrational. But being irrational is not a yes or no quality with nothing in between. Some irrational numbers can be approximated by fractions extremely well, snuggling up close to a simple ratio, while others hold the fractions at arm's length no matter how hard you try. And there is a way to measure this, a way to ask of any number, how well can simple fractions pin you down? When you ask that question of every number in existence, one number comes in dead last. One number is worse than all the others at being approximated by fractions. That number is phi. To see why, we need a tool called the continued fraction, which is a way of building a number up out of a nested staircase of fractions. You start with the whole number part, then add a fraction, and in the bottom of that fraction, there is another whole number plus another fraction, and so on down, each layer nested inside the last. Every number has such an expansion, and the expansion is like a fingerprint. Here is the crucial fact. When the whole numbers far down in that staircase are large, the number can be approximated very well by chopping the staircase off early, because a big number in the denominator makes the leftover piece tiny and easily ignored. Pi, for instance, has a large number early in its continued fraction, which is exactly why the humble fraction 22 divided by 7 works so well as an approximation to pi, close enough that school children have used it for centuries. Pi is, in this sense, fairly easy to approximate. Now ask what the continued fraction of phi looks like. It is the simplest and most monotonous continued fraction that could possibly exist. Every single number in the staircase is a 1. Not a large number anywhere, not even a 2, just 1, and then 1, and then 1, forever, an unbroken column of ones, descending without end. This comes straight from that self-referential arithmetic we found earlier. The fact that phi equals 1 plus 1 over phi, which if you substitute it into itself, over and over, builds exactly that endless staircase of ones. And because every number in the staircase is as small as a number can be, there is never a large denominator to give you a shortcut. Never a moment where chopping the staircase off gives you an unusually good approximation. Phi is approximated by fractions as slowly and as poorly as it is mathematically possible for any number to be. That is what the phrase means. Phi is the number that fractions can never get a good grip on, the number farthest from every simple ratio, the number that most stubbornly refuses to be pinned down. And now the two halves of tonight's story fuse into one, because I can tell you exactly which fractions do the best job of approximating phi, poor as that best is. They are the ratios of consecutive Fibonacci numbers: 2 over 1, 3 over 2, 5 over 3, 8 over 5, 13 over 8. Each one is the closest a fraction of that size can come to phi, the best possible approximation available at each level of the staircase, and the next one improves on it by the smallest amount any number would ever force. The Fibonacci ratios are not merely creeping toward phi by coincidence. They are the official best approximations to the least approximable number in mathematics. The whole numbers of the sequence and the endless irrationality of phi are the same fact stated two ways, one countable and one uncountable, one the shadow and one the thing. There is a theorem proved by the mathematician Adolf Hurwitz in 1891 that makes this rigorous and even a little poetic. Hurwitz showed there is a hard limit on how well any irrational number can be approximated by fractions, a best possible guarantee that holds for every number, and he showed that this ultimate limit is achieved by phi, and by numbers built like it, and by no others. Phi sits exactly at the boundary of what approximation can do. It is the number that pushes the theorem to its edge. Every other number is at least a little easier to trap. Phi is the hardest, the extreme case, the mathematical embodiment of refusal. It helps to see that phi is not alone in its family, only first in it. If instead of an endless staircase of ones, you build one out of endless twos, you get a different number, sometimes called the silver ratio, which is the second most stubborn number, harder to approximate than most but easier than phi. An endless staircase of threes gives the bronze ratio, and so on down a whole line of what mathematicians call the metallic means. Each is resistant to approximation, but phi, built from the smallest possible ingredient repeated forever, is the champion, the one at the very top. There is a reason the whole family matters. Numbers whose staircases eventually turn into all ones share phi's extreme resistance, and mathematicians call them noble numbers. When we get to orbits, it is precisely these noble numbers, phi and its close relatives, that will mark the most stable, longest surviving configurations in the solar system. The stubbornness is not a quirk of one number. It is a property a whole clan of numbers carries, and phi wears the crown. Sit with what that means for the sunflower, because this is where the whole thing stops being clever and becomes almost unsettling. It is one thing to know that the ratios of the Fibonacci numbers approach 1.618. It is another thing entirely to feel what it means that this particular value is the single hardest number in existence to approximate with a fraction. The number whose entire identity is a refusal to line up, a refusal to repeat, a refusal to fall into any simple pattern. And a plant, a growing head of tissue with no brain and no nerves and no notion of number, has settled its seeds around precisely that value. It did not settle there because phi is pretty. It settled there because it needed the one angle that would never let its seeds line up into wasteful spokes, and the only angle that never lines up is the one built from the number that never lines up. The plant is not decorating itself with a nice proportion. It is solving, in total silence, the hardest available version of the problem of how never to repeat yourself. The most stubborn number in mathematics turned out to be exactly the tool a flower needs, and the flower found it without looking. That is the genuine wonder at the center of this topic, and it is so much stranger and so much better than the myth we started with. Nobody had to write a code into the flower. Nobody had to teach it the sequence. The pattern falls out, unavoidably, from a growing thing trying to pack its parts without waste, because the mathematics of not repeating has a single best answer, and that answer is phi, which means we now have a real and solid piece of ground to stand on. In this one place, phyllotaxis, the golden ratio truly lives in nature, and we understand exactly why. So it is finally time to turn around and ask the harder question, the one that will occupy the rest of our night. If phi is this real, in a seed head, how much of the rest of the famous story is real too? The shell, the temple, the painting, the galaxy. It is time to bring a ruler to all of them, and to insist, at every step, on the one discipline that separates a real pattern from an imagined one, which is that a genuine appearance of phi should survive being measured carefully, while a projected one survives only as long as nobody checks. Part 7. Let us put the pieces together. Let us stop here for a moment and gather up everything we have found, because we are exactly halfway through, and the ground beneath us has shifted since we began, and it is worth standing still long enough to feel how far we have come. When we started, we had a claim, a big and comforting one, that the universe follows the Fibonacci sequence, that this simple list of numbers is a secret code written through all of nature. We took that claim seriously, and we followed it inward, and here is where it has led. We found first that the sequence itself is a human invention with a paper trail. It came to Europe in a merchant's arithmetic book in the year 1202, dressed up as a puzzle about breeding rabbits, and it had been known even earlier to Indian scholars counting the rhythms of poetry. There was nothing cosmic in its birth. It was a bookkeeping trick with an author and a date. We found, second, that hiding inside this list of whole numbers is a single irrational number, phi, the golden ratio, about 1.618. The ratios of consecutive Fibonacci numbers close in on it forever, without landing, and a formula ties the two together so tightly that the whole numbers are really just the golden ratio's shadow, its powers rounded off. The sequence and the ratio are one object seen from two sides. So the real question was never about a sequence of integers at all. It was about whether the natural world cares about this one particular irrational number. We found, third, that in one place it genuinely does. In the growing tips of plants, in the arrangement of leaves and seeds and scales that we call phyllotaxis, the golden angle appears for real, measured to within a fraction of a degree, and because it does, the spirals come out as Fibonacci numbers. This is not projection and not wishful measuring. You can count it yourself on a pinecone. And we found, fourth, why. The golden angle is the one angle that never lets a plant's parts line up into wasteful spokes, because it is built from full, the most irrational number there is, the number that fractions can never pin down, the number that most stubbornly refuses to repeat. A growing thing, packing its parts without waste, is solving the mathematical problem of not repeating, and that problem has exactly one best answer, and the answer is phi. We watched it emerge from a dish of oil drops with no life in it at all, which told us the pattern is not a signature of biology, but a solution that physics reaches on its own, and that living things simply inherited. So, here is where we actually stand. The comforting version of the story, the cosmic code, is already dead. Nothing is following a sequence. But out of its ashes has risen something better and stranger. A real and specific and beautiful fact about why one number, and only that number, shows up when things need to avoid lining up. That is a genuine piece of understanding, hard-won and solid, and we should not let anyone tell us it makes the world less wonderful. It makes it more. But notice what we have actually established, and notice its limits, because this is where the second half of our night begins. Everything solid we have found lives in one narrow place, the growing tips of plants. Phyllotaxis is real, and its mechanism is understood, and it is genuinely tied to phi. That is one island of truth. The trouble is that the popular story does not stop at the garden. It reaches much further. It tells you the golden ratio is in the spiral of a seashell, in the proportions of the Parthenon, in the geometry of the Great Pyramid, in the face of a beautiful person, in the paintings of Leonardo da Vinci, in the arms of a spiral galaxy, in the coils of your own DNA, in the rise and fall of the stock market. If phi is this real in a sunflower, the story says, surely it is real in all of these too. Surely the sunflower is just one visible thread of a code that runs through everything. That is the claim we now have to test, one case at a time, and we are going to test it the only honest way, by bringing a ruler. Because a real appearance of phi, like the one in the seed head, survives measurement. The angle is really there, to within a fraction of a degree, no matter who measures it. A projected appearance of phi is different. It survives only as long as nobody checks too carefully, only as long as you are allowed to draw the rectangle where you like, and ignore the parts that do not fit. The discipline that separates the two is measurement, and for the rest of tonight, measurement is going to be our blade. It is worth being clear about why the testing matters, and is not just debunking for its own sake. If the golden ratio really did run through shells and temples and galaxies and faces, that would mean one thing: a single mysterious code stamped everywhere by some unknown hand. But if the golden ratio appears only where a specific mechanism forces it, the packing problem in a seed head, and nowhere else, that would mean something entirely different, that phi is not a signature at all, but a solution, summoned only when a particular problem is being solved, and absent whenever it is not. Those two pictures could not be more opposed, and the only way to tell which one we live in is to go and look, honestly, at the places the code is supposed to be. If we find it there, measured and real, the cosmic code picture gains ground. If we find that the famous examples crumble the moment a ruler touches them, while the humble seed head holds firm, then we will know phi is a solution and not a signature, and we will know it not because someone told us, but because we checked. So take a breath, because the mood is about to change. We have spent the first half of the night building something up, finding the one place where the magic is real. We are about to spend part of the second half taking things apart, walking up to the most famous examples one by one, and asking them to hold still for the ruler. Some of what you have been told, some of what you may have repeated yourself, is not going to survive the next hour. And when the dust settles, we will find that the demolition has not left us with less, but with a clearer view of the one thing that was always true, and a path from that thing all the way out to the rings of Saturn. Let us start with the most beloved example of all, the one on the cover of 100 books about the golden ratio. Let us start with the shell. Part 8. The famous cases fall. The chambered nautilus is the single most reproduced image in the entire mythology of the golden ratio. You have seen it, sliced cleanly down the middle to reveal its interior, the chambers spiraling outward from a tight center in a curve of near-perfect regularity, and printed beside it, almost always, a golden spiral overlaid on top, the two seeming to match. Here, the caption says, "Is nature drawing the golden ratio with her own hand?" It is a beautiful image, and it is wrong, and the way it is wrong tells you almost everything about how this mythology works. The nautilus shell is indeed a spiral, and a very specific kind, called a logarithmic spiral. A logarithmic spiral is the shape you get when something grows by adding to itself in proportion to its current size, so that it enlarges while always keeping the same shape, curling outward at a constant rate. The nautilus grows exactly this way, adding new and larger chambers as it matures, each one a scaled-up copy of the last, and so its shell traces a logarithmic spiral. That much is true, and even lovely. But a logarithmic spiral can grow at any rate at all. The golden spiral, the one people overlay on the shell, is one particular logarithmic spiral, the one that widens by a factor of phi, about 1.618 every quarter turn. And the nautilus does not grow at that rate. When you actually measure real nautilus shells, dozens of them, their spirals widen by a factor of roughly 1 1/3 per quarter turn, not 1.618. The number is not phi, it is not close to phi. The nautilus is a logarithmic spiral, yes, but it is emphatically not the golden one, and the golden spiral printed on top of it in all those pictures has simply been drawn at the wrong size and rotated until it seems to fit, its mismatch hidden by making the overlay line thick and the photograph small. This is the pattern we will see again and again, so watch it carefully in this first case. The claim takes something genuinely true, the nautilus is a logarithmic spiral, and quietly swaps it for something false. The nautilus is the golden spiral, counting on the fact that the two look similar enough that no one brings a ruler. Bring the ruler, and phi evaporates. What remains is still interesting, a mollusk growing by proportion, but it is not the golden ratio, and it never was. Now let us walk up the steps of the Parthenon, the temple on the Athenian Acropolis, another favorite of the golden ratio books. Open almost any of them, and you will find a photograph of the Parthenon's facade with a golden rectangle drawn over it, and then more golden rectangles nested inside, and the claim that the ancient Greek architects designed the temple around Phi, that the divine proportion is the secret of its beauty. It is a lovely story. There is no evidence for it, no ancient text, no inscription, no account by any Greek writer says anything about the golden ratio being used to design the Parthenon or any other building. The proportion was known to Greek mathematicians as a piece of geometry, but there is nothing connecting it to the architects. And the rectangles drawn over the photographs, when you look closely, are placed with a suspicious freedom. Sometimes the rectangle starts at the bottom step, and sometimes part way up. Sometimes it includes the missing triangular pediment, and sometimes it stops at the roofline. The edges are chosen to make the ratio come out near phi, and the parts that do not cooperate are simply left outside the box. Measure the Parthenon honestly, edge to real edge, and you do not get phi singled out from the crowd of ordinary ratios you would expect in any large rectangular building. The golden rectangle over the temple was drawn in the last century or two by enthusiasts over a structure that never asked for it. The same fate meets the claim that the golden ratio governs the human body and the perfect human face. You will have heard that the ideal body has its navel dividing its height in the golden ratio, that the perfect face has its features spaced by phi, that beauty itself is measurable, and the measure is 1.618. In 1992, a mathematician named George Markowski published a careful paper taking these claims apart one by one. What he found is what you would expect. Human beings vary enormously. Navel heights, facial proportions, the ratios between one body part and another, all of them spread across a wide range from person to person. When someone announces that the average of these ratios is phi, they have chosen which points to measure between and which people to measure, and they have taken an average of a broad and messy range, and phi happens to sit somewhere in that range, along with a great many other numbers. It is not that human proportions cannot come near phi. It is that they come near almost anything, because they vary so widely. And singling out phi is a choice made by the measurer, not a fact forced by the body. And what of Leonardo da Vinci, so often named as the great artist who encoded the divine proportion in his work? Here the myth has a real seed, which is why it is worth handling with care. Leonardo did know about the golden ratio. He drew the illustrations for a book about it, a book literally titled On the Divine Proportion, written by his friend the mathematician Luca Pacioli, and published in 1509. So Leonardo was certainly aware of phi, but knowing about a number is not the same as building your paintings around it, and there is no evidence, none, that Leonardo composed the Mona Lisa or any other painting according to the golden ratio. The golden rectangles you see drawn over her face are, once again, modern additions, placed by later admirers who cropped and positioned them until they seemed to fit. And the famous Vitruvian Man, the figure inscribed in a circle and a square, is not built on phi at all. It is built on the simple whole number proportions described by the ancient Roman architect Vitruvius, whom Leonardo was directly illustrating. Ratios like the span of the arms equaling the height, nothing golden about them. It is worth knowing where the beauty myth actually came from, because it did not descend from the ancient world at all. The idea that the golden ratio is the secret of beauty, present in art and body and building alike, traces largely to a single 19th century German writer named Adolf Zeissing, who in the 1850s published sweeping claims that phi governed proportion throughout nature and art. He had no rigorous evidence, only enthusiasm and a willingness to see the number everywhere he looked, and his ideas spread because they were attractive, not because they were tested. A little later, a psychologist named Gustav Fechner ran experiments asking people which rectangle they found most pleasing, and reported a mild preference near the golden shape. But his results were weak and have never reproduced cleanly. From these thin 19th century roots grew the entire modern industry of golden ratio design law. The astrophysicist Mario Livio, who wrote the definitive book examining these claims, went through them methodically and concluded that the great majority are simply false, kept alive by repetition rather than measurement. The same collapse waits for nearly every other famous example. The Great Pyramid is often said to encode phi in the ratio of its slope, but the numbers depend entirely on which measurements you select, and other simple ratios fit just as well, and no Egyptian source mentions the golden ratio at all. Credit cards and standard sheets of printer paper are frequently called golden rectangles, yet a credit card's proportions are not phi, and a sheet of A-series paper is built on the square root of 2, chosen so that folding it in half preserves its shape, an entirely different and very deliberate ratio. Over and over the number is announced and, when checked, is not there. So 4 of the most famous pillars of the myth have fallen in a single hour, and they have all fallen the same way. Each began with something true, a real spiral, a real temple, a real body, a real artist, who really did know the number, and each smuggled in a false and specific claim about phi that could not survive being measured. The shell is logarithmic, but not golden. The temple is beautiful, but not golden. The body varies too much to be golden. The artist knew phi, but did not paint by it. And in every case, The golden rectangle, or the golden spiral, was something we drew onto the world afterward, and then admired, as though the world had drawn it for us. Which raises a question, at least as interesting as any fact about phi. If the pattern is so often not really out there, why are we so relentlessly, so universally, so happily convinced that it is? Part 9. Why we see it where it isn't. The reason we find the golden ratio everywhere is not out in the world. It is inside us, in the particular way the human mind is built, and understanding that is its own kind of revelation. Your brain is, above all else, a pattern-finding machine. It evolved to spot the tiger in the tall grass, the face in the shadows, the meaning in the noise, and it is spectacularly good at this. So good that it finds patterns even when there are none there to find. Psychologists have a name for this tendency to see meaningful structure in randomness. They call it apophenia. It is the same faculty that makes you see animals in clouds, and a man in the moon, and a face in the front of a car. And when a mind like that is handed a number as flexible as phi, and turned loose on a world as rich in measurable things as ours, it will find the golden ratio again and again, not because the ratio is there, but because the mind is built to find it. Two things make phi especially easy to find by accident. The first is that 1.618 is close to a great many ordinary ratios that turn up all the time. It is close to 8/5, which is 1.6 exactly. It is close to 5/3, which is about 1.67. It sits right in the middle of the range of proportions that human beings use constantly in design and construction and daily life. So any large collection of measured ratios, from a building or a body or a painting, will contain plenty of values near phi simply by chance. The second is that most real objects can be measured in many different ways. A face has dozens of features and hundreds of possible distances between them. A building has countless edges. If you are free to choose which two lengths to compare, and free to choose exactly where each length begins and ends, then with a little patience you can produce a ratio near phi from almost anything. The number is not rare enough, and the measurements are not fixed enough to make finding phi meaningful. Finding it proves only that you looked. Add to this the ordinary human tendency called confirmation bias, our habit of noticing and remembering the hits while quietly forgetting the misses. When someone measures a face and gets a ratio near phi, that measurement gets celebrated, printed, repeated. When the next measurement on the same face gives 1.4 or 1.9, it is simply not mentioned. The golden ratio books are full of the hits and empty of the misses, and so they build a powerful illusion of a pattern that the full, honest data would erase. You are shown the 10 photographs where the rectangles seem to fit, and never the 90 where it did not. You can watch this machinery run in the claims that phi hides in DNA and in the stock market, both of which fall apart the instant you look at the units. People say the DNA double helix measures 34 angstroms for each full turn and 21 angstroms across, and they note triumphantly that 34 and 21 are Fibonacci numbers whose ratio is near phi. But those numbers are only Fibonacci if you measure in angstroms and then round. Measure the same molecule in different units, or measure it more precisely, and the tidy Fibonacci numbers dissolve into ordinary decimals with nothing special about them. The pattern was an artifact of the units and the rounding, not a property of the molecule. The stock market claim is even emptier. Traders draw what they call Fibonacci retracement lines on price charts, levels supposedly set by the golden ratio, and sometimes prices seem to respect them. But they respect them only because so many traders are watching the same lines and buying and selling at them, which makes the prediction come true by making everyone act on it. It is not a law of markets. It is a crowd agreeing to bump into the same wall. There is one more coincidence worth diffusing before we move on, because it is a favorite of people who want the number to be magic. The golden angle is about 137.5 degrees. And there is a famous number in physics, the inverse of something called the fine structure constant, that is close to 137. The two numbers look similar, and so you will find claims that the golden angle in a sunflower is secretly connected to the most fundamental constant of quantum physics, that here at last is the bridge between the flower and the fundamental laws. It is a pure coincidence, and not even a very close one, since 137.5 and 137 come from completely unrelated mathematics, one from dividing a circle by the golden ratio, and the other from the strength of the electromagnetic force. That they sit near each other on the number line means exactly nothing. It is the same trick as the Nautilus and the Parthenon, two things that resemble each other closely enough that a hopeful eye can weld them together, and a careful eye pulls them apart. Underneath all of these errors runs a single, powerful wish, and it is worth naming plainly, because the wish is the real engine of the myth. We want beauty to have a formula. We want there to be a hidden order, a secret rule, a number that explains why some things please us and some do not, because a world with such a rule is a world that makes sense, a world we can master and trust. The golden ratio offers exactly that promise, a single tidy value that supposedly unlocks beauty in art and nature and the human form all at once. And the promise is so satisfying that people reach for it long before they check whether it is true. This is not stupidity, it is a powerful and understandable human hunger for order, the same hunger that built astrology and numerology, and 100 other systems that turn the messy world into a clean code. The golden ratio is simply the version of that hunger that wears the respectable clothing of mathematics, which is what makes it so much more persuasive and so much harder to shake. Notice, too, that the myth is nearly impossible to disprove to a true believer, and that is a warning sign in itself. Because phi is flexible and measurements are free, any counterexample can be answered by measuring somewhere else, by choosing different points, by insisting the ratio is really there if only you look correctly. A claim that can absorb any evidence, that can never be shown to be wrong because it will always find another rectangle to draw, is not a scientific claim at all. It is a faith. And the tell that separates the seed head from the temple is exactly this. The seed head makes a firm, checkable prediction. The divergence angle will measure near 137.5 degrees, and it keeps that promise every time, while the temple's phi retreats and relocates the moment you press it. One survives the ruler. The other only survives the absence of one. Now, there is a real feeling that comes with all of this, and it would be dishonest to skip past it. There is a quiet discomfort in learning how much of the pattern was never in the world at all, in realizing that the golden rectangles over the temple and the painting were drawn by us, after the fact, over things that never asked for them. For a moment, it can feel like a loss, as if the universe had just been revealed to be less enchanted than we were promised, as if someone had turned the lights up in a theater and shown you the plain walls behind the scenery. But sit with the feeling a little longer, and it turns over into something better. The wonder was not taken away, it was only relocated, moved out of the temples and paintings we projected it onto, and into the one humble place, the seed head, where it was quietly and verifiably true the whole time. We had been staring at the number in all the wrong places, chasing a reflection, while the real thing did its patient work in a flower by the fence, asking for no attention at all. And the moment you accept that, you are finally free to go and look at the places where phi is genuinely, provably real, and to find that they are stranger than any myth. We have one such place still waiting in the garden, and then a far more surprising one waiting in the sky. Part 10. The real cases are stranger than the myths. Now that we have cleared away the false examples, look again at the true one, because it has quietly grown more astonishing in the meantime. A sunflower places its seeds at the golden angle, and the reason is not that phi is beautiful, but that phi is useful, the one number that never lets the seeds line up and waste the space. We understand the mechanism. We have watched it emerge from a dish of oil, and yet knowing all of that does not shrink the wonder. It sharpens it into something almost uncomfortable. Because what we are really saying is that a living thing with no brain and no memory and no capacity for arithmetic of any kind has arrived at the single most mathematically special angle in the entire circle, the one built from the least approximable number in existence. And it does this reliably, generation after generation, in gardens all over the world, tonight, while we talk. Think about what that means. Nobody solved this problem for the sunflower. There is no gene that stores the number 137.5. No molecular ruler that measures it out. The angle is not written down anywhere in the plant. It emerges, fresh each time, from a simple physical rule, each new bump forming in the largest available gap, running over and over on a growing dome. The plant is not following an instruction to make the golden angle. It is following an instruction to avoid crowding, and the golden angle is what that instruction produces. Forced by the mathematics of the situation, exactly as surely as a dropped stone is forced to fall. The sunflower computes the most irrational number in mathematics, without knowing that numbers exist, the way a soap bubble computes the shape of least surface area, without knowing any geometry. That is not less than a cosmic code. It is more, because it needs no code at all. It needs only physics and patience. And here is the detail that clinches it, the fact that proves this is a genuine mechanism and not a mystical decree, and it is my favorite fact in the whole story. Sometimes the plants get it slightly wrong, and they get it wrong in exactly the way the mechanism predicts, and a magic code never could. Remember that phi is only the champion of a whole family of stubborn numbers, the metallic means and their relatives, the noble numbers. There is a close runner-up, a sequence built the same way as the Fibonacci numbers but starting from different seeds, called the Lucas numbers, 2, 1, 3, 4, 7, 11, 18, and so on. The Lucas numbers have their own limiting ratio, close to phi, but not identical, and their own slightly different divergence angle. And a small fraction of real plants, instead of showing Fibonacci spiral counts, show Lucas counts. Their growing tips settled into the second best attractor instead of the best one, the way a marble rolling into a landscape of dips can sometimes come to rest in a shallower dip beside the lowest one. We are not guessing about this. In 2016, a large citizen science project, coordinated through a science museum in Manchester, in England, and led by the mathematician Jonathan Swinton, gathered measurements of 657 sunflowers, grown and counted by volunteers across the country. The great majority of those sunflowers showed Fibonacci spiral counts, exactly as the theory predicts. But a real and measurable minority, nearly 1 in 5, showed something else. Lucas numbers, or doubled patterns where 2 spirals interleave, or near misses that sat just off the Fibonacci values. This is precisely what a dynamical attractor model predicts, and precisely what a cosmic code theory forbids. If the golden ratio were a law stamped into all of nature by some universal hand, there would be no exceptions, no Lucas number sunflowers, no doubled heads, no near misses. Laws do not have exceptions, but attractors do, because an attractor is just the lowest valley in a landscape of possibilities, and a growing plant, buffeted by the accidents of temperature and nutrition and timing, can occasionally settle into a neighboring valley instead. The exceptions are not failures of the theory, they are its signature. They are how you know it is a real physical process and not a fairy tale. The scatter shows up in other honest ways too, each of them a small confirmation that we are watching physics and not a decree. The direction of the spiral, whether it winds clockwise or counterclockwise, is not fixed by the mathematics at all. And sure enough, if you gather a pile of pine cones and sort them, you find left-handed and right-handed ones in roughly equal numbers, the choice made by some tiny accident early in each cone's growth. The counts are governed by the golden angle, but the handedness is a coin flip. Exactly as a mechanism would have it, and exactly as a rigid universal code would not. Some heads go further off the standard path and grow what botanists call bijugate patterns, built from two interleaved generative spirals at once, which doubles the visible counts to numbers like 68 and 110, still Fibonacci numbers but doubled, another neighboring valley in the landscape of possible arrangements. And the sunflower is not the only genuine case. Wander through the real examples and they hold up under the ruler in a way the temples and shells never did. The head of Romanesco broccoli shows the golden angle spirals nested inside themselves, each green spire a smaller copy of the whole cone, and each of those built from still smaller cones. A living fractal that repeats the same philotactic arrangement down through several scales. Cabbages, artichokes, succulent rosettes, the scales of many cacti, all show the same spiral counts arising from the same growing tip physics. Engineers have even borrowed the trick, arranging elements in phone tower antenna arrays and the mirrors of some solar power installations at the golden angle, precisely because it packs them evenly, with no repeating lines, the same benefit the sunflower gets, now deliberately copied by people who do know what a number is. When a mechanism is real, you can steal it, and you can build with it, and it will work in your hands the way it worked in the plants, because it was never magic to begin with, only mathematics doing what mathematics is forced to do. You cannot steal a myth, and you cannot build anything with it, because there is nothing underneath it to hold. So the honest picture, the one we have earned by bringing the ruler, is far richer than the myth we started with. The golden ratio is not a code written through all of nature. It is the solution to a specific problem, the problem of arranging things so they never line up and never waste space, and it appears wherever that problem is genuinely being solved and nowhere else. In the growing tips of plants, that problem is being solved for real, by the plain physics of parts avoiding one another, and so phi appears there for real, measurable, to a fraction of a degree, with just the scatter of exceptions that a real process should have. This is a fact you can hold in your hand and count on a pinecone, and it does not depend on anyone's faith or anyone's freedom to draw a rectangle where they like. But if the golden ratio is really the answer to a problem about not lining up, about avoiding resonance and repetition, then a thought should be starting to stir. That is not a problem that only plants have. All sorts of things in the universe need to avoid lining up, need to keep from falling into a repeating rhythm that would build up and destroy them. And if phi is the general solution to that general problem, then we should expect to find it not only in the garden, but somewhere out in the wider universe, somewhere with no biology at all, wherever nature is quietly solving the same puzzle by different means. It is time to leave the garden entirely, and to go looking for the golden ratio in the last place the mythology ever thought to check, in the cold mechanics of worlds moving around a star. Part 11. The same number, far from any garden. To find the golden ratio in the sky, we first have to understand a danger that every orbiting thing faces, a danger with a name that sounds harmless and is anything but. The danger is resonance. Imagine two objects circling the same star, or a moon and a ring of debris circling the same planet, one going around faster than the other. Now suppose their orbital periods fall into a simple whole number ratio, so that for every 2 trips the inner one makes, the outer one makes exactly 1. Every 2 laps, they line up again in the same relative position, and the gentle gravitational tug that the larger one gives the smaller one comes at the same point in the orbit, over and over, always in the same direction. A single tug is nothing, but a tug repeated at exactly the right rhythm, again and again, in perfect time, accumulates. The way a child on a swing rises higher and higher when pushed in rhythm. That is resonance. And over enough orbits, it can stretch and distort, and finally fling the smaller object right out of its path. You can see the wreckage this causes written across the solar system. In the belt of asteroids between Mars and Jupiter, there are gaps, regions swept nearly empty of rock, and they sit at exactly the orbital distances where an asteroid's period would fall into a simple ratio with Jupiter's, 1 to 3, 2 to 5, 3 to 7. At those distances, Jupiter's repeated tugs piled up and cleared the asteroids out long ago. They are called the Kirkwood gaps, and they are the tombstones of resonance, holes in the belt at every simple fraction distance. The same thing carves the rings of Saturn. The broadest gap in those rings, a dark lane wide enough to see through a small telescope, is called the Cassini division, and it sits where any ring particle would orbit in a simple 2-to-1 ratio with the moon Mimas, twice around for every one of Mimas's laps. Mimas, tugging at the same beat over and over, swept that lane clean. Let me set you down inside that gap, in the cold and the dark, so you can feel what a simple ratio does. Leave the garden entirely and stand inside the Cassini division, the dark lane that splits the rings of Saturn. Around you, the ring is not so much empty as swept, a corridor kept clean by a rhythm you cannot see. Out beyond the gap, the moon Mimas circles, and any boulder of ice that tried to hold an orbit here would meet Mimas's pull at the very same spot, twice for every single lap it made. A 2-to-1 beat, a push arriving on schedule again and again, always at the same point, always in the same direction. That is what a simple ratio does. It lets small pushes add up, one after another, until the boulder is nudged and stretched, and finally driven out of this lane forever, which is why the lane is a lane, and not a field of ice. Now drift inward, away from the resonance, into the crowded ring itself, and feel the rhythm fall apart. Here the pushes from Mimas no longer arrive on the beat. They come a little early, then a little late, then early again, scattered across every point of the orbit, never accumulating, cancelling themselves out over time. And so, here, the ice can stay. The safest place to be, in a universe full of gentle repeated shoves, is a place whose rhythm never quite matches anything else's, an orbit whose numbers refuse to line up. It is the very same instruction the sunflower followed, spoken now in gravity instead of tissue. Do not repeat, and you will survive. You can feel where this is going. If simple ratios are deadly, and safety lies in avoiding them, then the safest orbit of all, the most stable, the one most resistant to being torn apart by resonance, is the orbit whose period ratio, with its neighbors, is the hardest possible ratio to approximate by any simple fraction. It is the orbit whose numbers stay farthest from every dangerous whole number rhythm, and we already know which number that is. It is phi, the golden ratio, the most irrational number in existence, the champion of not lining up. The very property that makes phi useless for approximation, its stubborn refusal to sit near any simple fraction, is exactly what makes it the ideal for survival in a world of gravitational tugs. An orbit tuned to the golden ratio is an orbit whose pushes never fall into rhythm, never accumulate, never build toward destruction. This is not a poetic flourish. It is a real and rigorous piece of physics, developed in the middle of the 20th century by three mathematicians, Kolmogorov, Arnold, and Moser, whose initials give the theory its name, CAM theory. They asked which orbits in a gravitational system survive small disturbances and which fall apart, and they proved that the orbits most resistant to disruption are precisely those with the most irrational frequency ratios. Later, a physicist named John Green sharpened this to a fine point. Studying how order gives way to chaos as a system is pushed harder and harder. He found that the very last stable orbit to survive, the final one to break as the whole system tips over into chaos, is the one whose winding number is the golden ratio. Phi marks the boundary between order and chaos itself, the last thread to snap. The most irrational number is the most robust, the longest to endure, the final holdout against the descent into disorder. And notice, it is the same clan of stubborn numbers we met in the flower, the noble numbers, Phi and its close relatives, that mark these longest surviving orbits, the celestial counterpart of the Lucas number sunflowers. I should be honest that resonance is not always a wrecking ball, because nature is subtler than any single rule, and the honesty is part of what makes this real rather than mystical. In certain special arrangements, a resonance can actually protect an object rather than destroy it, by locking it into a rhythm that keeps it permanently away from a dangerous close encounter. The dwarf planet Pluto is caught in just such a protective lock with Neptune, circling the Sun twice for every 3 of Neptune's laps, a rhythm that guarantees the two never meet when Pluto crosses Neptune's path. So a simple ratio can be a cage that saves as easily as a hammer that shatters, depending on the details. But the broad landscape is exactly what KAM theory describes. Across the enormous middle ground of possible orbits, the simple ratio zones are lined with instability, swept into gaps and divisions, while the regions of safety cluster around the orbits whose ratios are hardest to approximate, closest to the golden mean. The exceptions do not overturn the pattern, they decorate its edges. The same mathematics reaches into machines that people build. In a particle accelerator, beams of particles circle a ring millions of times, and the engineers who run it live in fear of resonance, because if the number of oscillations a particle makes per lap falls onto a simple fraction, tiny repeated errors in the magnets accumulate lap after lap, and the beam is lost, flung into the wall, exactly as an asteroid is flung from a Kirkwood gap. So the operators deliberately tune the machine to keep that number, which they call the tune, away from simple fractions, steering it into the irrational safe zones between the resonances. They are solving the sunflower's problem again, on purpose, in steel and magnetism, choosing numbers that refuse to line up so that their beam will survive the way a stable orbit survives, and a well-packed seed head survives. Everywhere the same logic, the same reward for not repeating. Look at what has happened to our question. We went looking for the golden ratio in the sky, in a place with no life, no biology, no growing tissue of any kind, only gravity, and cold rock, and ice, and time. And we found it, doing the very same job it does in the sunflower, solving the very same problem, how to arrange a rhythm so that it never repeats and never destroys itself. The flower and the orbit have never met. They share no cause, no mechanism, no material, and yet they have arrived, separately, at the same number, because it is the one number that answers the one question they both, in their different ways, are asking. That convergence, across the widest possible gap in nature, is the strongest clue we have, and it points straight at the answer we have been circling all night. But before we claim it, there is one more territory to visit, a place stranger than a garden or a ring, where the golden ratio hides inside the structure of matter itself. Part 12. Where physics really keeps the number. There is a rule in the world of crystals that stood for a very long time, taught to every student as a certainty. A crystal is a pattern of atoms that repeats, marching in identical rows in every direction, and because it repeats, it can only have certain symmetries. It can be built on triangles, on squares, on hexagons, shapes that tile a floor with no gaps. But it can never, the rule said, have five-fold symmetry, the symmetry of a pentagon or a five-pointed star, because you cannot tile a floor with pentagons. Try it and gaps appear, and the pattern cannot repeat. Five-fold symmetry was forbidden to crystals, flatly and forever, and no one expected to ever see it. The first crack in that certainty came not from a laboratory, but from a mathematician playing with tiles. In the 1970s, the physicist and mathematician Roger Penrose discovered a way to cover an entire infinite surface using just two simple tile shapes, in a pattern that has five-fold symmetry and yet never, ever repeats. Slide the pattern in any direction and it will never line up with itself. It is ordered, deeply and intricately ordered, following strict rules about how the tiles fit, and yet it is not periodic, not a repeating wallpaper. These became known as Penrose tilings, and hidden inside them, governing the whole arrangement, is the golden ratio. The two tile shapes appear in the pattern in a proportion equal to phi, and the rules that force the tiles together at every scale are golden ratio rules. The reason it can be ordered without repeating is the same reason the sunflower's angle works, the golden ratio's refusal to fall into any repeating rhythm. Penrose had drawn, on paper, a kind of order nobody thought could exist, and phi was written all through it. Then, in 1982, an Israeli materials scientist named Dan Shechtman was studying a rapidly cooled aluminum alloy under an electron beam, and he saw something that the textbook said was impossible. The atoms were diffracting the beam into a pattern with clean five-fold symmetry, the forbidden symmetry, the pentagon symmetry, in a real solid piece of metal. His first thought, and everyone else's, was that he must be mistaken. The result was so contrary to the accepted rule that a Nobel laureate publicly ridiculed him, and he was asked to leave his research group for insisting on it. But he was right. He had discovered a genuinely new form of matter, now called a quasi-crystal, a solid whose atoms are arranged in perfect order that never repeats, the three-dimensional realization of exactly the kind of pattern Penrose had drawn. Quasi-crystals are ordered like crystals and non-repeating like the golden angle, and the golden ratio is built into their very structure, into the spacings and the symmetries of their atoms. Nearly 30 years after that ridiculed observation, in 2011, Dan Shechtman was awarded the Nobel Prize in Chemistry, alone, for seeing what everyone had told him could not be there. This is phi, appearing in physics for real. And notice how different it feels from the myths we tore down. Nobody had to draw a rectangle over a quasi-crystal and squint. The golden ratio is not projected onto it by a hopeful eye. It falls out of the mathematics of building an ordered structure that does not repeat, which is, once again, the exact problem the sunflower solves and the stable orbit solves. Five-fold symmetry and the golden ratio go together because both are ways of being ordered without being periodic, and matter, it turns out, can do this, can freeze into a pattern that is rigid and precise, and yet never the same twice. Quasi-crystals have since been found in nature, in a meteorite from Russia, and put to use in coatings that are hard and slippery, real materials doing real work, with phi in their bones. There is one more genuine appearance worth telling, because it reaches into the quantum world, and it is often wildly overstated, so it is worth getting exactly right. In 2010, a team of physicists, led by Radu Koldeya, studied a strange magnetic material, cobalt niobate, cooling it down and tuning it with a powerful magnetic field to the very edge of a quantum transition, a delicate balance point where its magnetism was about to change character. Right at that edge, they probed the material with neutrons and found that it rang, like a struck bell, at a set of specific energies, and the ratio between the two lowest of those energies came out very close to the golden ratio, 1.618. This was not an accident. It had been predicted decades earlier, arising from an intricate and beautiful piece of mathematics called E8. one of the most intricate symmetry structures known. The golden ratio appeared because that hidden symmetry demands it, at a precise and fragile point, in a carefully engineered experiment. It is not, as the headlines sometimes screamed, proof that quantum physics runs on the golden ratio or that phi is the code of the universe. It is something better because it is true, a specific, hard-won, elegant result in which phi emerges from symmetry exactly where the mathematics says it must. And there is a frontier where this may soon become useful in the effort to build quantum computers. Some of the most promising proposals rely on exotic particles whose behavior, when they are braided around one another, is governed by golden ratio quantities, so that the very stability of the computation would rest on phi, on the same refusal to line up that protects an orbit and packs a seed head. Even here, at the cutting edge of what human beings are trying to build, the number shows up not as decoration, but as function, because the problem being solved is once again the fundamental problem of order that resists collapse. There is a way of understanding where these non-repeating patterns come from that makes their strangeness feel almost inevitable, and it is worth a moment because it ties the whole idea together. A Penrose tiling, it turns out, can be thought of as a shadow. Imagine a perfectly ordinary repeating grid, the kind that does tile space neatly, but living in a higher dimensional space, 5 dimensions instead of 2. Now slice through that clean high-dimensional grid at an angle set by the golden ratio, and project the slice down onto a flat plane. What you get is the Penrose tiling, ordered because the grid it came from was ordered, but non-repeating because the golden ratio angle of the slice never lets the projected points fall into step. The golden ratio is the angle of the cut. That is why phi and 5-fold symmetry and non-repetition all arrive together, 3 faces of one geometric fact, and it is why a real material can freeze into this arrangement, because nature is only ever doing projection and packing, never magic. The quasi-crystals that resulted from Schechtman's discovery turned out to be more than a curiosity, which is another mark of a real phenomenon rather than a mystical one. Because their atoms never settle into repeating planes, they are hard, they resist wear, and they conduct heat poorly, and so they have been used in tough non-stick coatings and in specialized alloys, materials engineered on purpose around the golden ratio's refusal to repeat. And the natural quasi-crystal, the one found inside a meteorite that had drifted through space for billions of years before landing in far eastern Russia, was confirmed around the year 2009, telling us that the universe was assembling golden ratio matter on its own, in the cold of space, long before any human being drew a pentagon. That is as far from a projected myth as it is possible to get. Nobody was there to squint at it. It simply formed, ordered and non-repeating, with phi in its structure, because that is one of the shapes matter is allowed to take. Step back and survey what we have gathered. The golden ratio appears, genuinely and measurably, in the arrangement of seeds and leaves, in the stability of orbits, in the structure of quasi-crystals, at a hidden symmetry point in a quantum magnet, and perhaps in the machines that will compute our future. It does not appear, when you actually measure, in Nautilus shells, in the Parthenon, in the human face, in the Mona Lisa, in spiral galaxies, in DNA, or in the stock market. And the line between the two lists is not random. Everywhere phi is truly present, something is solving the same single problem. Everywhere phi is merely claimed, someone is drawing a rectangle. That pattern, that clean division running through everything we have seen tonight, is the answer we have been building toward, and we are finally ready to say it plainly. Part 13. The answer. So let us finally answer the question we began with, the one printed on the label of this whole idea, the one that has been waiting all night for us to be ready for it. Does the universe follow the Fibonacci sequence? The honest answer, now that we have earned it, is no. The universe does not follow the Fibonacci sequence. It does not run on a list of numbers, and it did not read Leonardo's book, and most of the famous places you were told to look for the code, the shell, and the temple, and the face, and the galaxy, do not contain it at all. Those were patterns we painted onto the world, and then admired as if the world had painted them. The comforting story of a secret numerical signature, stamped through all of nature, is, taken at face value, simply false. But that plain no is not the end of the answer. It is the doorway to a better one, because tucked inside the wreckage of the myth is something true and specific and far stranger than the myth ever was. The golden ratio, phi, the number the Fibonacci sequence is forever reaching toward, does appear in nature, for real, measurable to a fraction of a degree, in a handful of very particular places. It appears in the seeds of a sunflower and the scales of a pinecone. It appears in the orbits that survive around a star and the gaps that stay swept in the rings of a planet. It appears in the atoms of a quasi-crystal and at a hidden symmetry point in a quantum magnet. And in every single one of those places, without exception, phi is doing the same job. It is solving one problem, the problem of how to arrange things so that they never line up, never fall into a repeating rhythm, never resonate, never collapse into wasteful sameness. That is the underlying question, and the golden ratio is its answer, because phi is the most irrational number in existence, the number that most stubbornly refuses to repeat. It is, quite literally, the number that refuses to repeat, and that refusal is not a flaw. It is the whole point. It is the most useful property a number can have when the task at hand is survival, or efficiency, or order without collapse. So here is what is really happening, the truth that is so much better than the code. The universe is not following the Fibonacci sequence. The universe keeps running into the same problem, over and over, in places that have nothing to do with one another, a flower and an orbit and a crystal, and every time it runs into that problem, the mathematics hands it the same answer, phi, because there is only one best answer, and phi is it. The Fibonacci numbers are simply what that answer looks like when you stop and count. They are the tally, the visible shadow, the whole number footprints left behind by an irrational number doing its work. When you count 8 spirals and 13 spirals on a pinecone, you are not seeing a cosmic sequence. You are seeing the countable trace of a sunflower and a pinecone, independently solving the oldest optimization problem there is, and arriving, as everything that solves it arrives, at the golden ratio. And that is why the two images we have carried all night belong together, though they should have nothing to do with each other. On one side, a sunflower in a garden, turning its heavy face through a long summer afternoon, its seeds packed in their silent spirals. On the other side, a lane of darkness held open in a ring of ice, circling a planet more than 1 billion kilometers away, kept clean by a rhythm no one can see. The flower has no idea the orbit exists. The orbit was carved by gravity across an emptiness the flower will never cross. They share no cause, no material, no mechanism, no messenger between them. And yet they have arrived, separately and independently, at exactly the same number, because that number is the single answer to a single question that the universe keeps asking in room after room after room. How do you go on without repeating yourself? The flower answers it in tissue. The orbit answers it in gravity. The crystal answers it in atoms. And the answer, every time, is the number that refuses to repeat. Sit for a moment with how much this reframing gives back, because it can seem at first like we have only taken things away. We began the night with a universe that seemed enchanted, a cosmos humming with a secret number, and one by one, we stripped the enchantment out of the shells and the temples and the faces, until it looked as though we had left the world colder than we found it. But that is not what happened. What we did was trade a shallow enchantment for a profound one. The shallow version asked you only to be impressed, to nod at a coincidence and move on. The profound version asks you to understand, and in exchange it gives you something the coincidence never could, the sense of a single quiet law running underneath a flower and a planet and a crystal, not because someone wrote it there, but because the mathematics leaves no other option. A sunflower computes the most stubborn number in existence without knowing that numbers exist, and it does so for the same reason and by the same necessity that keeps a lane open in the rings of Saturn. That is not a smaller world. It is an enormous one, stitched together at the seams by pure logic, and there is a humility in it that the myth never had. The code story flattered us. It told us the universe had left messages for clever human eyes to find, that we were the intended readers of a cosmic text. The truth is grander, precisely because it does not care about us at all. The golden ratio was arranging seeds and orbits and atoms for billions of years before there was anyone to notice, and it will go on doing so long after. We are not the readers of the pattern. We are late arrivals who learned, recently and with great effort, to count the footprints and work backward to the thing that made them. The wonder is not that the universe is speaking to us. The wonder is that we, alone among all the things that carry this number, have figured out why we carry it and can stand in a garden holding a pinecone and see, in 8 spirals and 13, the shadow of the rings of a distant world. So the next time someone hands you a pinecone and tells you it proves the universe runs on a magic code, you can tell them something truer and more beautiful. The universe does not follow the Fibonacci sequence. It does something far more remarkable. It solves the same problem everywhere it appears, with no code and no plan and no hand guiding it, and it reaches the same elegant answer by pure necessity, in a garden and in the rings of Saturn alike. The pattern in your hand is real, and it is not a message left for us to find. It is the fingerprint of the universe, quietly doing the only thing it can, arranging itself so that it never falls into a rut, and leaving behind, for anyone patient enough to count, the simple whole numbers that are the shadow of the strangest and most stubborn number there is. That is not a code written into the cosmos. It is something the cosmos cannot help but do. And that, in the end, is the strange and quiet reason the same number keeps finding its way into the light, from the seed in your palm to the far cold edge of a ringed world turning slowly in the dark.